Okay, here we go then. So, systems of equations. That's what we're going to be starting off reviewing in these first couple of lessons. And so, let's just be clear on what we're talking about. This is going to be two or more linear... Oh, thank you. All right, hang on. We're going to do that. Thank you. All right. So, systems of equations. These are two or more, and we're going to look at linear equations, but we can have systems of all kinds of equations. But for our review, we're going to focus on linear equations. Our arithmetic sequences, right? Considered at the same time. We could say, in other words, for a graphing perspective, on the same coordinate plane. Or they'll be considered together as two algebraic expressions. Okay, now, we've got three types of solutions, right, for our systems of equations. So one type of solution we have is where there is an individual point, just put a dot right out there. And then we're going to draw just a, I don't know, just random line kind of going this way. Through our point. And then I want another line also going through that same point, kind of like this. And so we've got our two continuous linear equations here. And those two continuous linear equations meet at one location, right? And so we have one solution, or we could describe this as intersecting lines. Okay, so when we have these two straight paths and they intersect with each other, they meet at one point and only one point. And that is one solution for the system equations. One x and y value that makes both of those equations true at the same time, right? That's the idea. It's a point that exists on both lines at the same time. That's the idea. All right, now, when we have no solution, we have a situation that looks something like this. So we'll draw a line going this way. And then we'll draw another line like that. We have two non-intersecting lines on the same flat two-dimensional surface. We call those lines parallel, right? So these are our parallel lines. Anybody remember the difference between parallel and skew?
Skew would be on different planes.
Very good. Skew is on different planes, right? Okay. So they look like they're going to intersect, but they're not. They don't intersect, but they're not parallel because they sit on two different planes, right? So we talked about that in our geometry class. Good. Okay. And when we have a set of infinite solutions, we're going to draw a line. And then I'm going to pretend to draw another line right on top of it.
Wow.
Just like that. See how I did that? It's impressive, huh? Sleight of hand. That's what you're marveling at.
That's a great word.
So these are two concurrent. Here's a good word for you, Jack. Two concurrent lines, right there. No, it's not the same line. It's two concurrent lines. They have the same equations. They share the same points, but make no mistake, they are two definitely different. Well, not different. They're two of the same, but they're two lines. There's two of them. Yeah, it's not one line, even though it looks like one in the picture. So we have to make sure that we're clear that these are two concurrent lines laying exactly on top of each other, sharing every point in common and every non-point in common as well. Okay? Good. Three solutions, right? These are the three options when we're dealing with two of our linear equations. Okay, so as we get into this first question right here, I want to make sure that I'm clear in talking about something with you. Okay. Do I have? I think I have a. Okay. Quarter. Think of a quarter. Okay. On a quarter, there is the head side, right? It has a president on the head side, and then on the back side, you've got all these different representations of the different states, right? Okay. Two different visual looks when you look at heads versus tails on a quarter, same exact quarter. Now, if you're writing and moving ahead, that's not what I want you to be doing. I want you to stay focused with where we're at so you don't miss some important conversation and some important language, okay? All right, now, heads and tails, okay? I'm going to refer to the algebra side of things as the head side of the coin, and I'm going to refer to the picture side of things as the tails side of the coin. And so what you need to be able to make the connection with these and the rest of the things that we tackle in this class is that there is a head side, an algebraic component, and a tail side to all of these. There is a function representation with, numbers and letters, and then there is a visual representation of the function. And bouncing back and forth between heads and tails is going to be an important skill that you're going to need to have with all different kinds of functions in this class, okay? All right, so here we're talking about, how are we going to solve this by graphing? Well, we're going to graph these two lines. So what I want you to do is I want you to graph these two lines. They're both in slope-intercept form, so that should make it fairly easy. Graph those two lines and find where do they intersect. That's what I want you to do. Okay, go ahead. So you should have come up with something that looks like this. Now I have extra stuff written down over here. We'll talk about that in just a second. So I don't expect you to have that written down, okay? But what you should have done was said, okay, this first line, I'm going to start at -6, and then I'm going to slope down 5 and right 3. Or since I can't really go down 5 and right 3 because I'd be out here somewhere, I'm going to do the opposite of down and right, which is up and left. And so then I can slope up 5 and left 3 and get my line running here. Okay, and then with my other one, I'm going to start at +5, and then I can go up 1 and right 6 for my slope, and then I'm going to graph that line, and I find where these two lines intersect here at -6, 4. Now, I do want you to jot this down now, okay, because I want you to have some evidence of working with this to show this is why this works, okay? So what I've done here is I've taken these points, x and y, and I've plugged them in to each of the starting equations here. And then when I simplify them down, you can see that I get 4 = 4, which is a true statement, and 4 = 4, which is a true statement. And so if I asked you to prove to me that this is in fact the solution algebraically, this right here is what you would have to provide for me, showing that that one combination of -6, +4 produces true statements in both of those. We're good? Fraction math. Fraction math is going to show up a lot in this class, and so there's going to be a little bit deeper work on that fraction math. So if your fraction math is a little rusty, you might want to polish that up a bit. Okay, good. Moving on. All right. Let's solve by graphing number 4. Let's solve by graphing number 4. Now, keep in mind, you've got some different formats here, right? What format is this? Standard form. And standard form, the two key components for us with standard form are what? We're comparing two unique independent things, right? And one of the things that we use in standard form is none of one and all of the other, and none of the other and all of one, which are the whats? The x and y intercepts, right? And so that's what we want to try to graph from standard form if we can. If it's easy for us to do, then we want to do that. And in this case, it is. And then, of course, you have a slope-intercept form. So go ahead. Give it a shot. See what you can do. You should have come up with something that looks like this right here, right? And so you can see, like, with my y-intercepts, right, I'm just dividing off by the other number, right? So, like, for my x-intercept, if y is equal to 0, then I'm going to divide -12 by 3. And for my y-intercept, if x is equal to 0, then I'm going to divide by 6. So I'm going to end up with these 2 points, which I graphed here, and then drew my line. And then with my slope-intercept form, I started at -5, and I went down 1, right 2. And again, remember with the slopes, right? If it's negative, it should always have this downward left to right read to it. And you can keep in mind that this negative can either be assigned to the top or to the bottom. Not both, right? But we can assign it to the top, and we can go down 1 and right 2, or we can assign it to the bottom, which would be +1 over -2. That's up 1 and left 2. Same idea, okay? But it wouldn't be negative over negative, because that would be a positive sloped line. Important to remember that, okay? Okay, now, we could do this as well, though. Let's just take this standard form here, and let's put this standard form into slope-intercept form. So the first thing I'd want to do is I'd want to move my x over to the other side, like that. And then what's the next thing I would do to go to standard form from here, or to go to slope-intercept? Yeah, we're going to divide by 6 on both sides, and we're going to divide everybody by 6 over here. Now, sometimes we'll write this with 1 bar and 1 6 underneath, and you'll need to know that that means that I'm dividing like this 6 here by both terms, okay? Or we can write it with 2 separate 6s like that. And then when we simplify and clean this up, we get y is equal to -1/2 x, and this is going to be -2. Okay. We'll come back and talk about that more in just a second. All right. But this is parallel lines. How do we know they're parallel lines? Like, how do we know they're not just tilted ever so slightly that, like, way out here somewhere they're going to intersect? What's that? The slope is the same, right? Exactly. So, and we can see that, right? We can see that the slope is the same. And what? Because, I mean, isn't the slope the same with these 2 lines? Okay, so the slope is the same, and the y-intercept is different. Okay, so there's really 2 things, right? There's the slope being the same is one key component, and then the y-intercept being different is the other key component for our parallel lines or our no solutions. Okay, good? All right, let's do number 6. Okay, let's do number 6. See what you come up with. This right here. So I needed to divide off the -1 here to get it in slope-intercept form. And then here, I kind of flip my equation around and I divide it off to 3, because slope-intercept form is going to always have a +1 y out in front. And then you can see what I end up with is the same equation, right? So this is slopes are the same and the y-intercepts are the same, right? Okay, so that language is going to become important for us. So let's talk about some. Pretty good here? Any questions? Yeah.
So y can never be negative.
Not for slope-intercept form, no. Yeah, it's always positive. Yeah. Otherwise, we'll end up graphing from the wrong y-intercept. All right, now. We need to be able to classify these with a little language. And so I'm going to say see below for our classification. And this kind of goes along the lines, if you recall, about our, triangle classifications, right? There was acute, and then like we had the angle measures, right? Acute and, equiangular and obtuse. And then we had the sides, right? Like equilateral and isosceles and scalene. So we gave it 2 names, right? So we could have like, an acute scalene triangle, right? And so there was the multiple names. We're going to see the same thing here with these situations. Okay, so the classification for this one is called independent, consistent. Independent, consistent. You have independent lines. They're different from each other. But they're consistent at one point, the solution. So when we have a system of equations with one solution, we call that an independent, consistent system. How do we identify that? We identify that by two lines with different slopes. Okay? So two ways to identify it. On the tails side of the coin, if the lines meet at one single intersection, that's an independent, consistent system of equations. However, if we're looking here at the head side of the coin, the algebra, if we see different slopes, so these are both in slope-intercept format, and you can see that the M here and the M here are different. You see different slopes, you can classify it as independent, consistent. Know what to look for? Okay, let's talk about this one. Any guesses?
Same.
Okay, so we've observed that this has the same slope, different y-intercepts. What do you think we might call this one? It's in the same vibe. Close. There's two unique lines, right? There's two different lines, right? So if there were two unique lines up here, we called them independent. Then there's two unique lines here. We should probably call those independent, right? Independent, inconsistent, because there is no solution for these, right? There is some logic to this math. We don't just make random stuff up often. Sometimes we do. So this is independent, inconsistent. This is the algebra 2 part, by the way. This is like giving some other language to it. Okay? How do we identify independent and inconsistent when we're just looking at the head side of the coin? Well, one thing is we have the same slope and we have different y-intercepts. Okay? So again, if you're looking at the tails side of the coin, you have parallel lines. If you're looking at the heads side of the coin, you have the same slope but different y-intercepts. If that's the case, then you have an independent, inconsistent classification. Good? Everybody okay? Tell your neighbor what you think this one's going to be. Let's see what you got. It's in the same vein. It's in the same language. What do you think it's going to be? What do you think it's going to be? What have I said that these words refer to? The first one referring to the separate lines. The second one referring to solutions. All right, you ready? You should have told your neighbor that this is a dependent, consistent system. How many people got that right? Yeah? Dependent. Okay, we do not have two unique lines, right? We have two lines that are the same, and they do have solutions. Every single point is a solution. Every single point is in common, and so therefore our consistent tag applies to this because they have solutions between them. They have common points. So it's dependent and consistent, okay? And again, how do we identify that? That is going to be, looking on the algebra side of the coin, that's going to be the same slope and the same y-intercept. Those are really good assessment questions. Here's a system of equations. Is that, dependent, consistent, independent, inconsistent, dependent, inconsistent?
Is there not option?
Well, let's think about that for a second, right? So that would be like dependent, inconsistent, right? Could you have two lines that are dependent and not share any points? Maybe if they sat on different planes. But we're not really into three-dimensional stuff here. We're just dealing with basic linear equations on a two-dimensional coordinate plane. So
what makes a line independent?
It's whether it's the same line essentially sitting on top of each other. Those lines are dependent on each other. They're the same thing. Whereas each of these two lines are different lines, whether they're parallel or whether they're inconsistent, or consistent, those lines are independent of each other. It's easier to think of the lines being independent of each other and dependent more like together.
Yeah.
Independent, separate, dependent, together. Yeah. That's an easier way of thinking of it. Okay, good. Classifications and being able to solve by graphing, right? All right, good. Okay, that's the first part of the review. Okay, let's talk about solving by substitution. Yeah, I guess those will work for instructions. I don't know. Sometimes the instructions are a little funky, but the idea being here is that we want to solve one equation for one of the variables. We're going to isolate a variable. Then we're going to take that and plug it back into the other equation. All right, so let's just start with this first one, number 7 here. So you can see that this system of equations, and sometimes these are like bracketed like that. Sometimes you'll see them bracketed like this. And that just reminds you to consider these at the same time. So what we're saying here is the value of y is the same thing as -7 times some x number minus 1. Here we're saying the value of y is the same x minus 9. These two things are both the value of y. So we can substitute one for the other, right? So we can take this here and we can swoop that right in there for y. And so then we can say that -7x minus 1 is the same thing as x minus 9. And then we can solve that equation for x. Go ahead and do that. We have that solved for x, right? That's the value of x. Okay, so now we're going to take that value of x and we're going to figure out the value of y. And we could use either one. It doesn't really matter, right? So I tend to use the one that I think is going to be the easiest. So for me, I would go like this. Right? Okay, well, what did I find there? X and Y, but yeah, but what did I find there in terms of the tail side of the coin? Anyone, what did I find on the tail side of the coin? Nadia? A point? What do you mean a point?
Okay, you found you found the y-intercept and the x-intercept?
The y-intercept and the x-intercept. No. Ray? It's what? The lines intersect? Yeah, it's where do the lines intersect, right? Like what? But give me it like as an yeah, like what it would look. Tell me what it would look like. Like how would I write those two answers together? So like that, and then comma what? Like that. That's the answer. Yeah, that is the answer, right? That's the one point that makes both of those equations true. If you plug in 1 here and -8 over here, you're going to get the same true statement, just like we did in that first example here, right? When we were doing that with those fractions here, it's the same idea. We could plug those in and get that same value, right? Okay, classify that. Go. Independent, consistent. There's actually really two ways you could have known that, right? From the get-go, you could have looked at both of these that are in slope-intercept form and said, hey, I've got two different slopes. That makes it independent, consistent. Or I have one true solution, right? And if I have one and only one solution, then that makes it an independent, consistent system of equation. Yeah? Everybody okay? Good. All right, then let's do number 9. So we got to figure out how are we going to do this by substitution. Now we're practicing substitution. We were practicing graphing earlier. Here we're practicing substitution. So which of these equations do you think is going to be easier to use for substitution? The second one? Right, because we already have a positive 1y here, right? Okay, so what we want to do is we want to rewrite this second one here like that. And then we're going to use that to solve for the x variable. So why don't you do that on the left side, and then find the y value on the right side if there is one, and then let's see what you come up with, and then we'll classify it. Go ahead. See what you got. You can see if you're moving in the right direction, this is where you should have been heading right here. Yeah? Again, what I did was I took this right here and I replaced it for that y right there. You can see there's the 6x minus 5y. Distribute. Combine like terms. Solve. Now that I have one of the variables, I can use that to go back and find the other. I chose the second one. I thought the second one was going to be easy to use. You can use the first one too.
So once we have the x, we can plug it into
Either one of them, yeah. Yep. Because remember, this x has to be the same as this x.
Okay, I understand. Yeah,
If that's not the case, then we don't have a valid problem. Yeah.
Sounds good.
And then again, this is a single solution, so it's an independent, consistent answer. How about it? Good? Okay? Ish? Okay-ish? Okay? We'll practice some more. You'll get some more practice. But again, you have these notes, and then they'll be on the video as well that you can go back and review and just look at and be like, okay, let me follow along, let me rewatch this and make sure that I got this down. So if you're struggling with, some of this, then you can go back and do that as well. All right, let's talk about number 11. So, number 11. You could look at this in a couple of different ways in terms of which one is easier to solve for the particular variable. I don't know. I kind of think the first one is. I mean, then I don't have to deal with negatives. You could do the second one, but I'm going to do the first one. I'm going to divide everybody by 2. So that's going to give me y is equal to 3x plus 5.
Looks oddly similar to the one we bought.
It's got some similarities to it, huh? Okay, well, let's take that and let's plug it in. So again, what we're doing is we're taking this right here and we're substituting it in for that y right there. So let's do that. I've gotten here. Did you get here? Okay. So now if we're going to combine like terms, right, I can combine these together, and then that's unlike, right? And this is actually a positive 3x, right? So if I had 3 apples, and I took away 3 apples, how many apples do I have? I have no apples, right? My apples are now gone. Which leaves me with negative 5 is equal to positive 5. Is that true?
No.
Yeah, it's not. That's an illogical statement, huh? Negative 5, owing $5 and having $5 is never going to be the same, right? So this is a false statement. And when our variables eliminate each other and we're left with a false statement, there is no solution. Classify it. Visually, on the tail side of the coin, what type of a picture are we looking at? Are we looking at lines that cross each other? Are we looking at lines that never cross? Are we looking at lines that lay right on top of each other? What are we looking at here? Visually speaking. Okay, so these are parallel lines then, right? Yeah, these are parallel lines, right? Because there's no solution. There's no point in common on either of these 2 lines, right? Okay, so then in this case, then if it's parallel lines, then we have an independent and what? inconsistent system. Yes.
So we're going the next step and doing 0 equals 0. I guess you can't do that.
But 0 does, so see, there's no solving to be done here, right? I mean,
Both on one
if
side.
you let's just say you added 5 to this side, what would you have to do over here?
You can't, 'cause
Well, yes, you could. If I added 5 here,
it'd be 0 to 10.
0 equals 10. Is that a true statement? That's not true either. So in either case, you still end up with a false statement.
Report to the front office.
Okay?
Jackson, please.
All right?
Please.
Good so far? Okay. Let's do number 12. Hey, the good news is one of those is already solved for y for you. And we're doing substitution, so yeah. Let's see what you got.
So can we solve the x?
Here's what you should have come up with right here. Yeah? So this time, our variable eliminates itself again, right? But what are we left with? We're left with a true statement this time. 15 is the same thing as 15. And when we're left with a true statement, then that's because we have two of the exact same equations. And that makes our infinite solutions, our two lines that sit on top of each other. They are dependent and share every point in common, and they're consistent. Dependent and consistent. So this is what you're looking at on the head side of the coin. Tail side of the coin, head side of the coin. And at the same time, we're reviewing two different methods for solving systems of equations. We learned 3. One of them is solve by graphing. We're going to graph the lines. We're either going to have an intersection, we're going to have parallel lines, or we're going to have the same line sitting on top of each other. That's solved by graphing. And here's the thing. I'm going to ask you to use each of these tools. Okay? So I'm going to give you a problem, and I'm going to say, solve this one by graphing. I'm going to give you a problem, and I'm going to say, solve this one by substitution. I'm going to give you a problem, and I'm going to say, solve this one. What's the third method?
Substitution. Oh, prior. We have prior.
Prior knowledge. Activating prior knowledge right now. That's what I'm doing.
Some of repetition.
Elimination.
Multiple choice.
Okay, we'll get there. That's the next lesson. Okay? Solving by graphing, solving by substitution, solving by elimination. 3 different tools you need to know how to do. That's what we're reviewing. Okay, and then we're going to kind of take it to the next level with the elimination one. Okay? And then also the classifications. Good? Okay, what I want you to get in is some practice on this. Okay? So, I'm going to give you some time to start on your homework. That way you can just get some practice in. That's the goal. You've got 6 of each. 6 graphing and 6 substitutions. Okay? Whichever one you think you need the most work at, maybe you start with that one here in class, and you can ask questions if you can help.
What?
6 graphing, 6 substitutions.
Wait, really?
Yeah. No, those are just examples on the notes. We're not doing all the examples on the notes.
So not like last week.
Mm-mm. Cutting it down a little bit. Yeah. I know, right? I used to be so mean, huh?